Okay, this is second video of the assignment on 31, chapter 6-3, and sampling without a replacement. The question is, an airline has just finished training 25 first officers, 15 male and 10 female, to become captains. Unfortunately, only 8 captain positions are available right now. So airline manager decide to use a lottery to determine which pilot will fill the available position. Of the 8 captains chosen, 5 are female and 3 are male. Okay. Problem: explain why the probability that 5 female pilots are chosen in a fair lottery is not. Okay, so let's write down the equation. Okay, probability of success is out of 8. Okay, 5 trials, right? Okay, I'm sorry. It's the out of 25, it's 8 choose 5. Okay, 8 choose 5. And definition of success is choosing a female. That's 5. Okay, and definition of failure is choosing a male. It's ironically, okay, that's complement of 40%, so it's going to be 60%. So if 5 positions are female, so the leftover is 3 male, right? So 3 is the exponent is 3. Exponent is 5 for the success. That's 12.4%. Just remember this. Okay. But however, the correct probability is 10.6%. And I tell you why, because this is a solution, supposed to be this way. The manager are sampling without replacement when they do the lottery. When 0.4 chance that the first pilot selected for the captain position and the female. Once that position is chosen, the probability that next pilot selected will be the female is no longer 0.40, right? Matter of fact, what is that? So out of 25, female was chosen, so it's going to be 14 out of 24, because first lady is going to be chosen, right? So the binomial formula assumes that the conditional probability of success stays constant at 0.40 throughout the 8 trials on the chance process. This calculation will be approximately correct if the success probability doesn't change too much, as long as we don't sample more than 10% of the population. Okay, in this case, manager are sampling 8 out of 25 pilots, almost 1/3 of the population. That explains why the binomial probability is off by 17%, which is 0.018 over 0.106, okay, from the correct answer. All right, so now let's see. So the normal approximation to the binomial distribution. Okay, as n gets larger, sometimes interesting thing happen to the shape of the binomial distribution. Okay, this is out of 10 people, okay, when success was 80%. Look, it's the bin of the histogram is kind of thick. Now it's 20 bin became thinner. If n is 50, it's really steep. Means it become a little bit compact. No, there's no gap here so much, and become nearly normal, right? So that is the important fact. Okay. Histogram of the binomial distribution was n equal 10, and p equals 0.8. Everything is 0.8. N equal 20, n equal 50. Okay. So when n is large, we can use normal probability calculation to approximate the binomial probabilities. Here are the fact. Okay. So this is the condition you remember. Okay. All right. The condition is right here, actually. So I will highlight the condition, and you will use this condition for next chapter too. Okay. By the way, the 10% condition we will use next chapter too. Okay. So the mean is mu x, which is n times p. That's expected value we have been studying. Okay. The standard deviation sigma sub x is square root of n times p times failure, 1 minus p. That's the same thing. As a rule of thumb, we will use a normal approximation when n is so large that, so this is a condition, okay? I hope you remember this, and I will stop the video here and we go to next problem.